Okay, welcome everyone to this week's TAOS seminar. It's a great pleasure to introduce our dear colleague from Brookhaven National Lab, Arthur Sedlacek. You see here the title of his talk. It's all about a really hot topic, biomass burning, wildfires, which has consumed, a lot of media attention, science attention. You think about last 2 years, the burns and on the West Coast, in Oregon, California. So we will learn a lot about aerosols and wildfire composition. Before we come to that, a few words to Art. He is in the Environmental and Climate Science Department at Brookhaven National Lab. Some of you may collaborate with colleagues there. He's also the technical manager of the Aerosol Direct Effect Group. And so a little bit to his, education, because like me, he changed paths quite a bit. He got a bachelor degree in chemistry in the University of Wyoming, then did his PhD in physical chemistry in the University of Utah, joined as a postdoc PNL at 1992, and there he was interested in energy transfer between highly excited molecules, a little bit different, but then established, and that here comes the relevance and the bridging towards the atmospheric sciences. First ever remote sensing program at BNL he established and worked with that, and that culminated in 1999. He invented, and he got a patent for that, a short-range LiDAR for non-contact detection of bioaerosol chemical stuff that's used for natural disaster mass hazmat responses. And of course, this kind of photospectroscopy, and if I say LiDAR, many people here will recognize that that's an important tool in atmospheric sciences. And then after that stint, he joined the Climate and Environmental Science Division in 2004. He's interested, especially black carbon, brown carbon, these kind of brownish clouds, chemical transformation, optical properties, microphysical properties. He attacks that on various levels in the field, in field campaigns, on planes. He's so busy, we hardly see each other because he's always flying around and measuring. And so it's really great, long overdue to have you here. Tell us about your science. Thank you.
Thank you. We still have the one bar on top.
It's coming back.
Yeah. Okay, you hear me? Terrific. Daniel, thank you for the introduction and the opportunity to talk about some of our work here. For those who actually play in the aerosol community, some of these intro slides will be a little bit redundant. Be patient. We're going to get to the good stuff, but it's for the benefit for those who actually might not be familiar with aerosol itself. The goal today is to kind of give you an idea of biomass burning. We all know what it is, but why we're interested in it. And one of the things I want to get through here is we do primarily field studies, but oftentimes these field studies help motivate some laboratory studies. And I'll touch at the very end some of the stuff that we're doing in the lab that's really been motivated by what we've seen in the field. Okay. Why are we not moving?
Your clicker doesn't work?
No, I'll try this. All right, we did that. Okay. Well, it's not going away, is it?
Anyone knows how permanently remove this video control? It always comes in.
This one should we do it here.
Just below that.
Okay, let's see if that's safe. All right. So this slide is just kind of an intro to this subject. We still see these debates going on with climate change. And often there's several reasons for these debates, whether it's political motivation, economic motivation, miscommunication or messaging. But I want to touch upon here just real briefly as an introduction. It's a difficult scientific problem that we're actually trying to address here. And okay, did I cursor down? I was drawing cursor down, but having no success. Now we are. Okay, there it's not a page. So to kind of put this in perspective of why it's a difficult scientific problem, let's just look at this very simple schematic here. The sun is blanketing us with about 342 watts per meter squared. Okay, all that about approximately 30% is reflected back into space. leaving about 236 watts to be absorbed in the atmosphere on the planet. We have this big planet here that actually is absorbing this, and then takes that energy, converts it into infrared long wave, it's then emitted back. We have some trapping done by the clouds, but nominally we have about 236 watts per meter squared going out. So we have an equal system in equilibrium here, right? Amount of energy coming in equals amount of energy going out. Now let's go ahead and fast forward to today. And what we've done now, we've got some greenhouse gases in there, which now they're contributing about, or taking away, or helping trap about 3 watts per meter squared. So now we have a situation where the energy absorbed is not equaling the amount of energy actually going out. We have some extra wattage there. And in this case, we have a radiative forcing of about +3 watts. If you look at the pre-industrial CO2, about 280 parts per million, we're well over that. We're now, I think, even over 415 parts per million. But this 3 watts to the greenhouse gases is about 1 degree in increase in global climate change. So that's a big deal. The other thing I want to point out is this 3 watts, right? This change of 3 watts compared to what's coming in or what's absorbed, 236 watts. You're looking and trying to define and quantify a problem at the 1% level. So very little change in the amount of energy being absorbed or altered in this equilibrium is causing a 1 degree change. That's a difficult scientific problem, especially for a dynamic system like we have here. So if you look at this problem, well, I'm not going to write it. So that's right. Ooh. All right. Oh, wow. What the heck is going on here? I discovered a new button I didn't know I had. So here, what we're looking at is trying to understand the contributions to this increase in global climate change, global climate temperature. So here we're looking at the surface air temperature anomaly. And what we've done here by anomaly is we've defined the nominal temperature between 1851 and 1900 is by lead. And that's the black line here. That's the actual data. And then what they did is they did a calculation saying, we know what the CO2 concentration is in other greenhouse gases. Let's go ahead and calculate how warm the planet should be. And that's the red line here. And clearly, something's not quite right there, right? We're actually should be warmer than we actually are. So we need to understand what's going on here. You'll see how this motivates some of our work. Now, they actually went ahead and said, okay, let's look at what aerosols can do, because aerosols are primarily scatterers of incoming radiation, so they scatter light back. And so again, here's a black line is our actual data, the green is the aerosols. And what you see is you see a pre-industrial, and then you see this massive dip. So what we're seeing is an offset compared to the greenhouse gases with respect to what the aerosols do with the incoming radiation and the surface temperature. So what they did is they said, let's go ahead and combine these things. And sure enough, what you find very quickly is it really is the combination of greenhouse gases and the mitigating effects of aerosols that need to be accounted for. So we need to be aware of this. And to kind of put things into perspective, we talked about greenhouse gases adding about 3 watts per meter squared, and the radiative forcing for aerosols about a minus of 1 watt per meter squared. Again, very, very small numbers considering what we're playing with. Now, aerosols are a unique creature and very different from molecular species. They come in a variety of sizes. They can be composed of a variety of molecular species that make up the particle itself. They can exhibit very different radiative forcings. I'm kind of showing you this plot here, where all these different, first of all, the blues represent more of a cooling effect, the red an absorbing effect. Here you have ammonium sulfates, which primarily are white, and hence they will be reflective of incoming solar radiation. Black carbon is black, it's going to absorb, it's going to behave just like a greenhouse gas. But as you can see, all these different materials have different optical properties and have exert different effects. The aerosol size and composition actually impact how they actually behave with the light, interact with the light. And finally, the atmospheric lifetime is on the order of days to 2 weeks, in contrast to, say, greenhouse gases, CO2, which would be decades. So what do I mean by aerosols? This is just a simple cartoon, just kind of put it in a size perspective. I took this from the EPA. This is a human hair, down to about 100 microns in size. The blue here represents a PM particulate material 10 microns in size, the blue dots. We zoom in, we got PM 2.5. Those who do a lot of environmental studies recognize these particular metrics. That's 2.5 microns. We zoom in again, I superpose 5 little black dots. That's about a 500 nanometer particle. We actually work in this level at about 500 nanometers and less. So we're actually working very, very small species. Aerosol sources can be both natural and anthropogenic. Natural can be dust, forest fires, sea salt, pollen, volcanic eruptions. In contrast, anthropogenic can be agricultural burning. You got to burn the crop stubble after you've harvested. Industrial, classic there, biofuels. And so and the other take home message here is all aerosols are efficient scatterers of light. A subset of them are actually very good absorbers. That's what we're going to go ahead and focus on here. So, wildfires. First and foremost, they are critical to the ecosystem. They are a good thing, right? They remove decay and dead material, decaying material, dead material. They clear out underbrush. They release nutrients back into the soil to be used. They can help start the germination of seedlings. Similarly, though, they can account for about 40% of the black carbon inventory in the atmosphere. In fact, wildfires drive the year-to-year variability in aerosol loading in the atmosphere in the mid-latitudes. And of course, we have a situation, we have warming temperatures, which is drying out the vegetation, which is extending the wildfire season. And now we're also seeing that there's being an increase in the number of fires and the intensity of that fires. And what does that do? Well, that's a positive feedback loop, because now we're actually increasing the temperature some more because we're releasing greenhouse gases and other aerosols that can absorb, which is further warming the temperature. So these things are pretty critical and important for us to try to understand these things. Wildfires, again, as I kind of pointed out, are complicated little species because they can do lots of things simultaneously. And I like this photograph because it demonstrates that. So here's a fire. You can see the crowns actually actively flaming there. And right above that, you see the black stone, primarily composed of black carbon, right? It's black, it's absorbing. But at the same time, look at all this white stuff there. So we're actually generating from the smoldering that's occurring right around the active burning some other aerosols. So we actually have absorbing aerosols being generated as well as pure scatterers. And our job is trying to make sense of this. And then if that's not complicated enough, we have the fact that the chemical, microphysical, and optical properties can change as a function of age. So once they're created, they can still undergo changes. And if they change composition, that could change their optical properties and how they interact with the solar radiation. So it's really a pretty difficult problem, which is a fun problem to actually tackle. I like this plot. This is a number of fire detects from Modis, from Ralph Kahn, NASA. Every one of those dots is over the course of a 10-day period. Every one of these dots represent a single fire detection. So this is basically gets across the fact that fires occur everywhere and are quite ubiquitous. And if you go ahead and integrate over the entire year, basically anywhere where there's ground, there's going to be some burning. So we need to understand these things. If you just to be clear, if you zoom in here, I'm not saying all of Central America is burning. It's just a resolution of the dots. But the fact is, you have a lot of wildfires everywhere occurring. Getting stuff that helps motivate some of our work. This was taken again from NASA. This is during the height of the pandemic, September 2020. And if you recall back then, there were a lot of raging wildfires in California. And in fact, those wildfires are actually impacting us here in terms of air pollution. And so here's a nice little image showing an optical image showing where the plume is. Here's the fires out here, but they're affecting all the way across. In fact, they're circling back around the St. Louis there and impacting us. So clearly these fires that occurred 3,000 miles away can affect over and start influencing us. So this starts begging some questions, especially as I pointed out, that they can change. How are they changing and what's going on there? Video wildfires is a little bit longer here. Here's a nice image again taken from NASA. This is from Modis. You can see the burn ring right there. It's amazing the resolution that these satellites have. You can see the burns right there. See some part of cumulus there. You see this big area here. What's kind of hidden, or which is kind of difficult to see, is a scale. That's about the size of Manhattan burning right there, which is pretty remarkable. And so you're looking at it about almost, a little over 21 kilometer fire breadth there. And that's just one fire occurring up in Alaska. So these things are pretty significant. And so with that comes a lot of injection of emissions into the atmosphere. And finally, there's health effects. So there's a number of people looking at this for different venues. we at Brookhaven are interested in understanding the radiative forcing contributions of wildfires, and that's what drives us. So my colleague, Larry Kleiman, and I put together a project proposal and then something conducted a project called BBOP, the Biomass Burn Observation Project. And our goal here is to try to understand what happens to these aerosols right at the source, right at the fire, those first couple of hours after emission. We actually flew aboard at the time was G1 aircraft, DOE sponsored program. This is a photograph of a wildfire we actually probed in Idaho. And over here is a collection of all the 21 wildfires that we actually sampled during one portion of the campaign. So how do we actually go about actually looking and probing the aging of these things? Because after all, we're actually doing an experiment out in the field as opposed to controlling things in a laboratory. So we do this via a pseudo-Lagrangian type approach. So here I've overlaid here on this image of a plume, a flight transect. And the idea is that you're flying orthogonal to the direction of the plume, and right over the plume, we'll call that T equals 0. So now if the wind speed is about maybe 20 miles per hour, let's go downwind about 20 miles, and then go ahead, go back over the plume. And as long as the emission is pretty constant, this is a pretty good approximation in terms of actually studying the aging. So over the course of those 20 miles, for a 20 mile an hour prevailing wind, we have about an age of 1 hour. Then we do it again at 40 miles, do another transect, we go 2 hour old air. And so this actually works remarkably well in terms of giving us a handle on what's going on. A couple photographs of our system itself. Again, that's G1. This is what our inlets look like. So we're actually flying through the plumes. You have to bring the material into the plane, into the instruments themselves. This is what it looks like. And in some cases, it's almost standing room only because our instruments take priority and we want to jam as many instruments as we can. And over here is a native looking camera, there's a 100-meter reference there, what it looks like down below. For those who have very good eyes, you'll see that there's a helicopter down there. And while we scientists are actually probing the flames, the U.S. Forest Service is trying to put out the fire. So it's a very interesting interplay between allowing us to do our stuff, but actually staying out of their way. And I always use this opportunity to thank our pilots for getting us safely there and back. So some of the things we actually measure, we look at several properties of aerosols. We look at their size distribution, right? What their sizes are, their ability to uptake water, which is important for clouds, influencing clouds. What are their optical properties? How do they scatter? How do they absorb light? And then composition, chemistry. What's that source? How does that change? So we take a lot of measurements. These are just a couple of examples. I won't go into detail on them. But suffice it to say, we actually deployed 18 instruments on this aircraft. So we jammed a lot of instruments in here. And because you only get one pass, you do an experiment on one day, one flight, and that's it. It's different, maybe no longer present the next day. So you want to get as many measurements as you can. Last of the photos here. This was a fire that Larry and I actually went ahead and probed. Over the course of 24 hours, it burned nearly 5 square miles, about a quarter of Manhattan. Over just 24 hours. Over the course of its lifetime, it consumed 18 square miles. And this is actually what it looked like. That's what it looks like on the outside. That's what it looks like on the inside. And that's not a retouched photo. It actually has kind of an orange hue to it, given all the absorption scattering taking place inside there. So let's go ahead and look at what we found looking at these things. I'm going to kind of focus on 2 things: the formation and evolution of tar balls. It's kind of shown over here, and then the evolution of black carbons. I think that especially its latter portion, I think we can use as a metric for probing the lifetime and some of the behavior that happens with these particular plumes. So here are tar balls. This is actually a TEN grid. You're seeing the lattice structure of the grid itself. That's the actual size. It's a person's thumb right there. These little black dots are the tar balls themselves. It's taken from a VDOT data set. Tar balls, despite their name, are not tar. Okay. But they do exhibit broadband absorption spectra similar to black carbon. They're composed primarily of carbon and oxygen. They're about 100 times smaller than fine beach sands. Kind of give you an idea how small we're talking about here. As you can see here, they're uniquely identified with microscopy in the sense that they're spherical in shape. This also tells us something, that the fact that we can impact a particle onto a grid and maintains its shape tells us it's pretty viscous. It's not changing its shape when they're in action. And right now, tar balls are the only way of microscopy is the only way of detecting tar balls. So we have to go ahead and play as best we can. For those who might be in the marine community, I just want to point out that wildfire tar balls are not beach tar balls. So if you actually have the interaction of oil from a spill oil tanker interacting with salt water, you can get emulsion that comes on the beaches. That's also called tar balls. They are not the same thing. Okay. And I say that because a program manager wanted me to point that out once. All right. So back in 2005, Jenny Hand published a paper where she was using microscopy at a fire that was raging outside the Yosemite Valley. And she was noticing that when she actually looks at a grid and counts up the various particles there, that in the middle of the smoke plumes, when they're impacting the site, they're getting a lot of these tar balls. That's these red bars right here. All right, we have green for non-volatile, pink dust, black carbon is the soot, and then the organic is the blue. And so there's a propensity of seeing a lot of these tar balls. The other thing is, under these events, she often saw that 70% of the particles she actually saw were tar balls. So that's a remarkable event to create that many tar balls. Now, the problem, of course, with microscopy, for those who play with it, is you're collecting stuff on a grid. First, you have to store it. So if there's very highly volatile material, that material is going to evolve and go away. Then you actually take it to your microscope. You got to work under a vacuum. Again, semi-volatile material can go away. And so what you're getting is a biased opinion here. So a biased measurement. So 70% is an upper limit. It's probably lower because we've lost some material that we can't actually measure. So that was a state of affairs. But nonetheless, this plot says that tar balls potentially can be important. So we actually went ahead and looked at that. And we combined a couple of techniques to actually get around some of the issues of microscopy. Remember, microscopy is the only way we can actually measure tar balls. Yet I want to try to understand and quantify the loading of tar balls. So here's our grids. This is right over the fire. Again, this lattice structure is the lattice itself that we collect the tar balls onto. There's nothing that looks spherical there, yet 2 hours later, our grids are peppered with it. So what we did is we combined this, because the other thing that microscopy measures very well is black carbon. So what I did is I have another instrument called SP2, single particle spectrophotometer, that actually measures black carbon. And I can actually get out what the mass concentration or the mass loading of black carbon is. And I can use microscopy to give me a ratio of tar balls to black carbon. Combine those two, I can get an idea of what the loading is for tar balls. And that's what I show you right over here. So looking at the mass, the tar ball mass fraction as a function of plume age, 2.5 hours of aging over here, right? Again, doing these Lagrangian transects. And what you notice is right over the fire, I want to draw your attention to the center column right here. Right over the fire, we're not seeing any tar balls. Right? Koji Adichie was working with us, couldn't find any tar balls there. But as we start aging a couple hours, we start to count more and more tar balls. And indeed, when we use this technique of combining the SP2 with the microscopy, we're able to quantify this. So we see no tar balls, zero fraction. By the time we get about 2.5 hours old, upwards of 40% of the mass is actually tar balls. Now, what's interesting here, and I'll point out here, here's what we call an upwind measurement. Think of this as residual aerosol from another day or a couple of days old. And so our measurements are consistent in terms of getting some terminal value of loading. Now, what's interesting here is the plot below. Here I'm looking at the enhancement or change in the organic aerosol. That's what OA stands for, over CO. CO is inert, so we treat it as an inert tracer. It corrects for any kind of dilution that the plume may be happening. And what do you see? There's not much change there. So what does that tell us as a scientist? What that tells us is that we're not creating new particles, but we're transforming some particles. So what Larry and I came up with is this moniker of calling tar balls highly processed primary particles. So the primary and sense are created right over the fire, but then they undergo some kind of compositional change to become these guys right here. So once we're armed with this, we suddenly can do a lot of fun stuff. And one of the big things, again, DOE is interested in radiative forcing, right? So what we did is we recognized very quickly a lot of people have looked at tar balls, but because they didn't have the information we did, they couldn't do certain things. And one of the things you discover is that a lot of people are saying tar balls are as black carbon. If you look at the imaginary component of the index of refraction, they're saying tar balls are just about as black carbon. At the same time, there were people out there that says, no, 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 no. Tarballs are like 2 orders of magnitude less black than black carbon. Somebody's got to be right, somebody's got to be wrong, right? So what we did is we recognized that we actually could look at this. We actually had measurements, optical measurements that we could provide. So I'm using the single scattering albedo, which is simply the scattering over the extinction. And we're going to look at that as a function of plumage, just like we were talking about. And then we went ahead, and Larry did a lot of this work. We went ahead and said, okay, I know what the mass loading of tarballs are. I know what the mass loading of black carbon is. I know what the mass loading of OA is. I know what the refractive index is for each of those species. Let me calculate what the SSA should be under these 4 limiting cases for the refractive index. And when you would, and again, overlap with this is the fact we know we're producing more tarballs as we get older. And sure enough, there are 2 that really stick out, that if the tarballs had a refractive index making them as black carbon, the SSA should have dropped down as a function of age, but it doesn't. Indeed, it actually ticks up a little bit, which is consistent with some of the studies that said tarballs, the measuring component of tarballs indicates it's closer to what we call brown carbon, but not black carbon. And so that was a significant finding. Indeed, if you go take it a step further, you can actually almost argue that while black carbon is significantly more black than tarballs, right? Indeed, is 40 times darker, if you will, than tarballs. The fact that we're producing so many more tarballs than black carbon, right? About 40% of our mass of these blooms is tarballs. Only a couple percent is black carbon. What you find out is that tarballs can contribute all by themselves about half the absorption. So even though they're minimal in terms of their absorption, there's so many more of them that we can actually have a significant contribution. Now let's take this. So now we've been looking at near field stuff. And so this kind of helps spur me to start branching out and ask what happens as these guys actually start aging. So in a paper that was published last fall, we put forth this idea that there are several regimes when you can actually look at the aging of these biomass ferns. There's this local regime, regional regime, and global regime. Over a local regime, you're going to be sensitive to the source fuel. You're going to be sensitive to the burn conditions. Are you flaming? That certainly favors more production of black carbon. Are you smoldering? You're not actively flaming, so you're cooler. You're not driving the reactions all the way to black carbon, so you're getting more OA. You get pyrolysis. There's a lot of dilution and cooling taking place. A lot of chemistry can take place there. You got coagulation, condensation. Coagulation, particles come together. Condensation, they kind of grow on top of a particle. There's POA, primary organic aerosol evaporation. We formed a POA right over the fire, but as it cools, it can start evaporating a little bit. Get into the regional regime. So now we've diluted to a certain extent. Now we have competition between chemical and microphysical processes. Are we evaporating? Are we changing the shape of these particles? We have photochemistry can start taking place. You have secondary organic aerosols that can start being produced. We have production of brown carbon, polymerization. And then if we go to still a step further and ask what's going on globally, because remember, aerosols can last 1 to maybe 2, 3 weeks. What happens as we go further? Well, you can get brown carbon bleaching. You can actually bleach out some of the chromophores that are responsible for absorption. You have material loss due to volatility, cloud processing, and of course, there's wet and dry deposition. And so what we decided to do is use this technique of this single particle cyclotometer, SSP2, and the fact that black carbon is inert, it doesn't change as a function of age, as a way of using it as an internal standard, and then use it as a probe of age. And how am I going to do that? Again, black carbon doesn't change with age. But as I pointed out, we get condensation or coagulation of organic material on that core. So if we can come up with a way of actually measuring what's happening to this organic coating around that core, we have a way of actually probing these things. So in the simple cartoon here, I have coagulation condensation. There's an idea of coagulation. This little branch structure is black carbon. It's an aggregate. The green represents an organic aerosol. Coagulation just came together. Here's the condensation. That's what's going on. What we're going to do is we're going to make it really simple for ourselves, primarily because the instrument allows me to do this in a straightforward way. I'm going to take these things, I'm going to treat them like this. So I'm not going to distinguish between a coagulation or condensation, but I am going to go ahead and leverage the fact that I have a very sensitive technique that allows me to work within the limits of this function of what we call core shell morphology. We have a black core, when we have a uniform coating around that core. And all I'm going to do is I'm going to go ahead and monitor the change in that coating thickness or the amount of coating mass relative to the black carbon core mass as a way of actually probing how these things are changing as a function of age. So how are we going to actually do this? This is the oh, thing. Let's see, this way. One more, I think. Right? Okay. So this is the SP2 itself. Pretty boring instrument to look at, but if I dive inside, what I have here is I've got the big laser beam operating at 1064 nanometers. All right, and here I are. Here's my coated black carbon particle. As soon as it enters in that laser beam, the first thing it does is scatter some light. So you have a channel that actually measures the scattering of light. And we can actually use that scattering signal to tell us something about the coated BC particle diameter, the entire BC containing particle diameter. However, as this particle continues to go deeper and deeper in the laser beam, right, it's a Gaussian laser beam, black carbon particles absorbing the light, it's heating up. Eventually it burns off the coating, leaving just the black carbon core, but it keeps on absorbing to the point that it actually burns up, boils, and gives off an incandescent signal. We can then go ahead and calibrate the incandescence to a mass, and from the incandescence, we can get a black carbon particle diameter. You combine the two, and now you have a measure of how much coating is there. So I'll be talking about this metric of using this mass ratio of coating to black carbon core. So here's some stuff from Bebop, near field, okay, right over the fire basically. So looking at the mass ratio of coating to a 100 nanometer core. So I'm gone ahead and taken one slice of my size distribution, said, okay, I'm looking at those black carbon particles that are 100 nanometers in diameter, and ask how does the mass on that particular particle change? Over the course of this case, this is a different fire. This is a course of almost maybe 150 minutes. And sure enough, what you see is that mass ratio is ticking up actually pretty quickly. And that's not too surprisingly. If you look at a biomass burn, what do you see? A massive plume. That plume is opaque because there's a lot of material there that can go ahead and condense. So we're seeing basically almost doubling or 2.5 times increase in the amount of mass on these coatings. So what I did is says, okay, let me go look at all many of my Bebop data sets. And so we could start getting this picture. So, and you're going to see a lot of this particular plot going on as we go on. So we're going to look at the mass ratio of the coating to 100 nanometer core as a function of plume age. This is in days now on a logarithmic scale. And so here's a whole bunch of different flights from the Bebop data set. And one thing that sticks out to you, there's two things. One thing that sticks out to you is they're all trending up, or they're getting a little bit thicker as a function of age. The other thing that strikes you, boy, there's a lot of scatter there, right? What's going on? What we speculate on is two things. One, these are all represent different fires. So there could be a source fuel dependence on there. We don't know, we don't control what's burning down there. We're actually going out and actually making measurements in forested areas. And two, we don't have any control of the burn phase. So some of these could actually represent a lot of active flaming, some could represent smoldering, or a combination thereof. But they all are tracking in the same direction. That is, they're getting thicker or more organic masses being deposited onto the particles. Now, I've taken that, and then I went to the literature and I said, okay, for those that have made some studies out there, can I go ahead and populate this plot a little bit more? And it turns out there's been some studies, and I kind of cite those down over here. And so now we're starting to get a picture, right? So we see that in this right over the fire, there's this rapid increase in the amount of coating around these cores. And then all of a sudden, things kind of stop. Now, why might they stop? Well, they could stop simply because we've exhausted the available material that can actually condense on there, right? We're diluting all the time. So there might be a natural point where we actually stop. And so now we're starting to get a picture here. So now you can just see where we're getting these regimes. So here's what I would call that local regime. We're seeing a lot of rapid growth. I'd argue we're now in a different regime where there's a cessation of growth, right, to other processes. And this starts begging this question here, which we'll get to. It's interesting to note that the blue and dark cyan colors here actually represent two studies using the same data set. And so this shows you just some of the discrepancies of how people analyze the data. But nonetheless, there does seem to be a nominal slowing down or cessation of the growth. So the question then becomes, what happens now? Do we just stay out there and stay constant? Is there a further increase in the coating thickness? Do we come out and we start losing some coating thicknesses? And this is important because models actually need to understand on a global scale what has happened to these aerosol particles, right? So and so I want to point out here, to put things into perspective. So I've been talking about near field studies, right? BBOM. This is actually a flight track from BBOM. You see all our orthogonal transects there. This is where the burn was. That's the direction of the plume. All of this builds that one pixel right there. So it's not really representative of what's going on, right? It's really very local. And indeed, I showed you earlier today this, right? This is from that one graphic from NASA for the 2020 fires in California. And, you know, we made measurements with BBOP there, but we know that we're getting plumes that are transecting over several thousand miles. So clearly, we need to be aware of what's going on here. We need to be able to make some measurements there because we know they're lasting a long time in the atmosphere. So I had a very unique opportunity, truly unique opportunity of actually being part of a campaign with NASA called Oracles, where they're actually looking at very aged plumes affecting off the coast of Africa. All right, and we actually had another program at the same time that was staged in Ascension Island, in the middle of the Atlantic. So a couple pictures here. This is the Ryan P3 aircraft with the crew there. Here's the coast of Africa. There's Ascension Island, St. Helena, Napoleon Bonaparte fame, you might recognize that. So you're really in the middle of nowhere. Thank God for GPS. I wouldn't want to fly and not know where I'm at, that's for sure. And the idea is you got these burns over here, they're vecting over the ocean. That's about 1,000 kilometers. And so the question is, what's going on? How are they aging? Can we understand them? Here's a picture of Ascension Island. I'll give you an idea of what it looks like there. So now what we're going to do is we're actually going to use the same kind of methodology, only this time we're actually going to go forth and see if we can start populating our plot there. And sure enough, what we find, these are all our Oracle campaign slides, where using some high split and some very sophisticated aging tracer modeling efforts. We see they're actually sampling plumes that are in the order of 6 days to maybe 12 days old. Using the same methodology, what do we see? We see that in the slope regime, we peak out about a mass ratio of 20 times more coating mass than black carbon mass per 100 nanometer particle. Yet when we do the same analysis for the Oracles campaign, we see it massively dropped off. So clearly something is going on there. We're not going up, we're not increasing our mass ratio, and we're certainly not staying constant. So something's taking place. And the question is, what could be responsible? What could be driving this change in coating mass? Well, 2 processes, right? We can have some chemical processing or cloud processing. In the case of chemical processing, we can have catalysis. So let's say you've got some chromophore, say brown carbon, or a brown carbon that is a light absorbing organic aerosol. It can absorb photons. It can undergo photolysis. You generate smaller fragments of higher volatility. You go back in the atmosphere and you reach mass. You have heterogeneous oxidation. You can have oxidative processes that open up that can start chewing away at some of these species, breaking bonds and losing material. And you can also have some aqueous phase chemistry. So there's various venues that present themselves to account for the loss of material. You start looking at this, you can think, well, this is probably a slow, continuous process. We're slowly eating away at this as a function of age. Now let's contrast that to, say, cloud processing. So now we're going to take these particles, interact them with the plume. It's not cloud, excuse me. And so we can either activate, right? Not activate. If we activate, we wash out. There's going to be a step function. Those that are larger diameter particles will preferentially be activated. And if they're washed out, they're taken away from the distribution. And indeed, we see some evidence of that when we actually use, when we actually use a PCDI probe or CDI probe, excuse me, and the aircraft, which actually separates activated aerosols from non-activated. When you actually go in, when you typically make a measurement of these smoke plumes at Oracles, is the size distribution of black carbon. The nominal mode is about 115 nanometers. Yet when you go ahead and do the same measurements inside the CDI, you're seeing that mode is shifted to 144, telling us that we're preferentially activating these larger diameter particles. So again, part of this is we could be, in fact, stripping away either coating or preferentially activating and pulling away these particles. Now, the thing to recognize is, again, if it's clouds, it's going to be episodic. Either you interact with a cloud, and when you do, it's done, it's irreversible, it's over. So two very different things for us to look at. And so these different processes are in fact coming into play. And indeed, what we've done, and it's subtle here, but now I can point it out, is these measurements are all in the free troposphere. So I basically have eliminated one. I've taken cloud processing aside. I'm not going to worry about that just yet, because that's a complicating complication to our analysis here. So this coating loss is due strictly to some kind of chemistry, whether it's photolysis or oxidation. And indeed, I don't show it here. There's a paper coming out by one of my colleagues from University of Miami that shows that there's some brown carbon loss, there's some bleaching taking place. These things actually get a little bit wider as a function of age. And there is some evidence to suggest that there's some heterogeneous oxidation taking place. Now, the other thing we can do, I've been showing you the same plot I've been showing you, except I put in a linear scale instead of a logarithmic time scale. And this is actually very informative for us because this is what we had before. Come on, right there, right? Logarithmic, we have our local, regional, and now I would call this global regime. If I put it on a linear scale, you can see that the local is just that line right there. And indeed, even the regional is just that little sliver. So what does this tell us? This tells us that the lifetime of these aerosols are dominated by the slow loss of material. Over the course of 2 weeks, all this stuff happening in the first couple hours is important, but in the overall lifetime is not that important. And this is important for modelers. Do they want to get all this chemistry and physics and all the computation right, or they want to start, say, with a mass loading of 20, and then use, in this case, we've done some estimates of what the loss rate is, and then use that as a proxy for what's happening with the coating loss. I showed a couple of other comparisons here from paper by Jesse Kroll, where he's looking at some laboratory oxidation of some components there. And so we are certainly losing material a lot faster than he is, but a paper just came out by the UC Davis group, Xizang group in California, and they were actually measuring very aged Siberian smoke from Mount Bachelor Observatory, and their loss rate is even faster than ours. So ours is falling somewhere in between. But what is consistent here is this growing picture that as these things age, there's a steady loss of material. That's the take-home message of this. Now, let's just segue in the last few minutes that I have here, is we come back to this. So I hopefully have made an argument, hopefully a convincing argument, that there's natural regimes here of growth, cessation, and now we get this global regime. And one of the things that we want to ultimately we want to know is what's going on from the radiative forcing perspective. I've seen all these changes. What do these changes mean from radiative forcing? So let's go ahead and look at the local regime taken from our paper looking at the intervals. So this is just the same plot I showed earlier. So I stripped away all the other calculations. Here's our SSA. And we see this slow increase in the SSA as a function of age for the first couple hours. Shellac et al. Actually published a paper and came up with what they call a forcing fraction, or the radiative forcing is the expression here, as a function of, let's see, the most important things, the surface reflectance, surface albedo, if you will, single scattering albedo. Here you got an absorption and reflective component, which you're going to call the forcing fraction. And if I plot the forcing fraction as a function of SSA and a function of surface albedo, I get several isolines here. And so the question is, what is happening to these fluids from radiative forcing perspective? So if we're starting out fairly absorptive here, lower SSA and trickle up, we're going basically from here to here. And depending on what the surface reflectivity is, you can be going from, say, a warming condition, which is delineated everything in the bottom portion of this plot, to a cooling regime. So that's what's happening in the near field. Now what happens? I do this. Let's see what happens. Now let's go fold in the global stuff. Here we have a very different situation, right? Here the SSA is coming down. And indeed, what's happening, right? the black carbon is remaining. We have less coating around the black carbon, so the black carbon is exerting its absorptive behavior. So the SSA is coming down. We apply the same kind of logic here. I'm taking our canonical value about 0.94 from the near field measurements I just showed you, down to some terminal value about 0.82 for the SSA here. And so what you're going from, again, depending on what your surface albedo is here, and I give you a couple of canonical or boundary conditions here of post burn might be 0.05, nominal absorption might be 0.5, 0.15, and maybe 0.4. And depending on that, again, you'd be going from a cooling regime back to an absorber, positive forcer. So now we have this thing where we have a dynamic system that in the near term can become cooling, but as it ages, can come back and haunt us by adding to and contributing to warming like CO2. Finally, as I close out here, as I pointed out at the beginning, we do a lot of field measurements, but we use these field measurements to help motivate laboratory studies. And so you've seen this plot before, but I didn't talk about this stuff right down here. This is stuff that was conducted at LASIK. That was a ground station on such an island. And same kind of analysis. But here, these mass ratios are really very small. And the difference here is this is on the ground in the boundary layer, and this is in the free trouble. So this seems to be suggesting that there's other processes that can start again eating away at this. And indeed, I'd argue probably cloud processing is one of those. Remember, I purposely looked at free troposphere here earlier just to eliminate this. But here's a hint down here that in fact it may be very important. And so giving a plug to my postdoc, Ola, who's working, what she's doing is she's actually trying to create a cloud in the laboratory right now. So we have this ensemble of particles, this cartoon here, right? We have some black pores coated, some non-containing black carbon particles. In the field, they interact with the cloud. A subset of those will activate, potentially wash out. And at the end, you have some residuals here, right? So now we shift to smaller size. The thing that's absorbing is the black carbon, which remains. We're going to see a lot more absorption. What she's using a combination of a CCN and a pressure PBI, BCBI, to create an in-cloud or a benchtop cloud, if you will, in the laboratory, where she's going to try to simulate this, where we can actually measure what's residual and what's actually activated. And the idea here is, again, based on some of our LASIK data set, that there's some extra processing here. This is her laboratory, and I don't get to play with anything, I can tell you that, for fear of destroying it. But here's some of the data that she's starting to collect. And so in this case, we have a laboratory, and Daniel's familiar using surrogates. We love surrogates. And so we're going to use what's called Regal Black as a surrogate for collapsed black carbon. So that's a simplification. And then we're going to use levoglucosan as our organic material or organic surrogate for the OA that coats this for fresh BBA emissions. And what we're looking at here is the critical supersaturation of the functional mobility diameter. You can think of this as that point upon which we can just get activation to kick in. What is that critical value? The green here represents pure levoglucosan. The black here is uncoated black carbon particles. And what she's done, she started coating these things. We have a coating chamber, we can actually coat this. And what she's showing here is as you start coating these black carbon cores, they very quickly go from a condition where they're very difficult to activate. Again, the lower the supersaturation, the more easy it is to activate. So up here, we're having great difficulty activating, but just a little bit of coating. And some of these coatings are on the order of just a couple nanometers of coating. All of a sudden, these guys want to activate and start dropping down very quickly. And so this is something we want to look at, which again is motivated by some of our field studies. So in closing, I think our work has shown that wildfires exhibit a very complex life cycle. And that can be delineated into these regimes. In the near field, we showed you that we have these production of these things called tar balls. It's a very subclass of brown carbon fuel, right, absorbing organic aerosols that contribute 30 to 50% of the particle mass in some U.S. fires. And indeed, others have found a lot of tar balls. So it's pretty ubiquitous, I think pretty important species. We're using the coating thickness of black carbon to help us understand what's going on near field. And as we get more coating on these black carbon particles, they become more efficient scatterers. And that then takes us from a condition where we have more warming character to more cooling character in that near field. We contrast that to the global regime, where we have this very slow loss of coating on the black carbon particles. And what's happening is the scattering is dropping down and we're having a drop in the SSA. And this loss of coating makes these wildfires slip back from being primarily coolers to more absorptive species. And so the goal here is to understand this and parameterize this so modelers can actually start getting this complex behavior in there. So with that, I thank my colleague, Larry Kleiman, sitting in the audience. Again, I had a lot of fun doing this particular campaign. These are just some photos from the Bebop campaign. Dan Jaffe at Mount Bachelor was our ground site for that. I also want to thank the Oracles campaign. These are some snapshots of the campaign itself. We actually had a wingtip to wingtip flight with the Manchester group. So Pete might recognize the BAM aircraft as was Larry. This is the ground site that DOE actually had on Ascension Island, making some measurements there. And again, just some photographs. How many out there in the audience can figure out what these tire tracks are? On Ascension Island in the middle of nowhere. Turtles. You got it, that's right. And so it turns out Ascension Island has a lot of turtles that come to it. And so it was taken at midnight. And so it's, again, the beauty of what we do is we get to travel to all exotic places. And where else we get an experience like that. So with that, I thank you for your time. I'll be more than happy to entertain some questions.
Thank you, Art, for this really nice and intriguing overview talk. We have time for questions, so please, and folks online, I will check the chat. If you have questions, you can put questions into the chat, please. Mingwa.
Yeah, so the book, the question is naive when you said the carbons are not newly created, they were from the primary source.
That's right.
So why is that? Can't they be newly created after the fire?
Well, we think that they are OA that has undergone some kind of oligomerization, or colleague Alex Laskin in Indiana suggests that maybe there's some evaporative processes taking place, leaving less volatile material that becomes what we characterize as tar balls. And one of the questions I think for us is to understand, is there some kind of, again, we have brown carbon. Is there a photolytic process here? So one of the questions, indeed, Daniel and I were talking about this morning, is we could answer that question by doing a day-night measurements. If it's photolytic and tar balls form at, with the light, we can basically turn that off because that's what happens. And so we need to ask those kind of questions. Part of the problem is because we don't know quite how they're formed, we don't know how to form them and make them in the laboratory, right? Some people have taken a water tar emulsion and aerosolized and then flash heat it at 600 degrees, and all of a sudden pops out tar balls. Now, we actually used it in our paper when we talked about this to point out that that's not what happens. Because if that's what happens, the hottest part of the fire is right over the fire. And so we should have seen tar balls right over the fire, but we don't see that. We see them slowly grow in as we go downwind. So that suggests some kind of slower reactive process. So it could be photolysis, could be some kind of oligomerization that's initiated with some kind of reaction. Well, those kind of things are open questions. But we do know from the fact that the ratio of the OA, change in the organic aerosol loading to CO, which is our conserved tracer to correct for dilution, that doesn't change. So we're not creating something out of the atmosphere and putting more mass in there.
And then the other one is it's a really very nice process level for understanding. Do you know whether there are modeling efforts trying to calculate, say, what it is?
That's our goal. Forget the paper on it, to make people aware of it. What I can tell you is that the propensity is to use laboratory measurements or near field measurements. And the reason I do near field measurements is because they're easy to do, right? Being able to do measurements long range is difficult. So what happens is they will use those studies and use those mass ratios or mixing state properties as the basis and say that's constant. And all we're going to do is wash it out, but we're not going to account for the fact that the amount of CO, amount of organic aerosol mass can change the function of it. So we think this is going to be an important a study in the sense to highlight the fact that things change constantly. And as Daniel again and I were talking about, that you're gonna have transitions to various phases. So all this, it makes sense in the sense that nothing is static in the atmosphere. And we're really pointing out that because black carbon is conserved tracer, we use a tracer that's conserved, we can learn something that people haven't yet probed about. And again, it's a difficult study. I was uniquely positioned because I was with Larry studying the near field when the Oracle's campaign allowed me to participate. I had this unique position saying, oh, I get to see what's happening in the near field and compare that to what's happening on the other extreme. So I was in a unique position to say, wait a minute, there's something very, very funky going on here.
Thank you.
You bet. Yeah.
Hi.
Hey.
Think, me first.
Yeah, go first.
I really liked your talk.
Thank you.
I was wondering if you could tell us anything about the difference in the burning, what was burning between the oracles and the bebop.
Yeah, that's a good question, right? The general consent, well, we kind of have a good feel of what was burning here in mid latitudes, right? It's a lot of pine, softwoods, and that might be the unique mixture that's necessary for carbons, get this tarry emulsion material. In Africa, it tends to be crop burning, things like that. So that's the argument that we made is well, boy, you're looking at two different fuel sources. One of the things that we're exploring, indeed, is this argument. We believe that after a period of time, there's enough chemistry that takes place that a lot of these aerosols are going to lose memory of where they came from. By this, I mean memory of their source fuel. So we think that it's still reasonably good comparison to make, but we think there's two different sorts of fuels. And then, of course, if in fact it is crop burning that dominates in Africa, that's going to be much more flaming. And we know that if we have a hotter fire, we're going to generate more black carbon as opposed to organic. Say in the wildfires in the Northwest, we have this combination of smoldering, pyrolysis, and active flame.
Yeah, thank you for the presentation. What I understand is that you test solar pools near field and far field. Do you have opportunity to test solar pools as a different type of atmosphere?
No, and that's a great question actually, because there have been, it's hard to do ground-based measurements, and people have made ground-based measurements and done TEM. And what they found is that what I showed you in RTEM with these nice individual separated turtles, right, all by themselves. But what you find is on some ground-based measurements, they actually see coagulated turtles. And so is this generated because of the higher concentration of these things? And so there's a something question. So it's one of these things that, and if that's the case, our tar balls preferentially created under lower temperature conditions, right, more smoldering conditions, and hence stay lower to the ground and don't go off. So that's what most people, nobody's ever looked at the vertical distribution of tar balls, but we can kind of infer that there's something there to be sure. Yes.
Have you been able to look at any of the interactions between like what is used to put out the fires? Like, you know, some of the dusting and the aerosols.
That's a great question, and we haven't looked at that. So I think that, you know, every so often Larry and I would be looking at the data and get a really strange result. And we kind of said, oh, it must be that baby, all right? You know, we've never pursued it, but it's a valid question. And indeed, I think taking a step back a little bit, one area that I think is going to become profoundly important in terms of studying wildfires is this whole wildfire urban interface. As these wildfires start actually interacting and burning houses and communities, we're having different materials combusting. And so there's the obvious health effect, but also what's getting pumped in the atmosphere. But that's a great question. It really is. What be generated, how it's interacting with the material sorting in the atmosphere. But I can't answer it. Sorry.
All right, I have maybe two comments. So, and then you go for lunch. I'm really intrigued that the absorptivity is very high, and then increases and then decreases, low increase and then decreases in the far field. This is really a challenge for the climate modeling community then, all right? Not only that the absorption changes, gets less again due to the coating, no, more because the coating goes away. But then it also dilutes, or if I would ask you, what would be the background aerosol over the United States during fire season. You don't always have this dense plume, as
No,
you say,
that's right.
dilutes.
That's right.
So what do you put in a climate model? What is your mixture? Is there like 10% is highly absorbing, again, wildfire, then you have some sulfate, ammonium sulfate.
And then
That's
you went,
really a challenge, right? I mean,
and then you went into that, right? Let's say you now have some interaction with clouds, preferentially siphon out some of those, right? So now you get rid of the larger guys, and you're left with smaller guys. So it's terribly complex, but that actually makes it fun, right?
yeah, of course, we want challenges. And my second point is I'm working with an undergraduate in an honor season, looking at the health impact. She analyzed EPA monitoring stations around this terrible wildfires in the 2020-21. The concentration of PM 2.5 in some of these towns was over 200, 300 micrograms. Some sensors got damaged. There's no measurement. It's blank afterward.
Wow.
They're so blackened. And the federal limit exposure is something like 13 micrograms. Okay, so if you think about the complexity of the particles and this organic coating, this kind of gooey around the black carbon itself is carcinogenic. Or if you see the black carbon cloud out of a truck, you go internal ventilation. You don't want to get that in your car. And in some countries in Europe, that's forbidden. What you see here in the US, as a matter of fact, because it's such an adverse health effect. But around these fires in California, what people are exposed to, this is quite mind-boggling. So we have to understand the chemistry, the health effect with these data.
And indeed, I'll close with the fact that some colleagues of mine up at P&L and I are trying to put together a small little campaign where at P&L up in Washington, they're going to be making measurements in their facilities, basically being near field. And if the advection of these plumes is sufficient, we'll make some measurements here as a way of trying to grapple with these very long range agents, because it's a very logistically a very difficult set of measurements to make. I mean, Oracle's attempted to do it, but that was an expensive campaign. I can tell you that for sure. So we'll see if this has any traction. The idea would be to almost have a network of groups that make measurements, use some remote sensing with RSRs, if you will, go ahead and get a measurement of what's happening with the plume. And then if Mother Nature is kind to us and it comes and affects over us.
Yeah, and
they
they
submit
have
it.
to burn, right?
Then that has to it's been a question that comes to us.
All right, wonderful. Thanks. Let's
Thank
take
you.
it hard again for this great seminar.